Something tells me that wasn't no coincidence, huh?
Hello everyone, this is Benny and welcome to the first episode of the game algorithm series. If you are a kind of different game player who is not satisfied with only the visual representation of the game, but would like to dig a bit more detailed behind the scene, or maybe you've already had a plan to step into the game industry, then this whole series of tutorials is exactly what you need. So the material I plan to do are all here on the screen as you can see. Don't be scared by all the terminologies if you don't understand many of them. I will explain all of these step by step in a quite straightforward and intuitive way, and introduce, all these classic algorithms and designs to you guys. So we can start the journey now. For the very first episode of the series and the first chapter, I would like to talk about game terrain design and auto-generation. In games, all elements we may see in any perspective is part of the game environment, which is also a crucial part of the core idea design of a game. If the environment is designed to be simple, then the interactive opportunities for players are limited as well. If the environment is relatively complex, for example, many of the open world games we may see, then the actions from the players will be harder to predict, and the pressure for all the AI systems in the game will go high as well. Many of the terrain or landscapes we can see from the games are essentially mazes. Some of them are literal mazes, some are tunnels from the first-person shooting games, the city design from AAA games like GTA or Cyberpunk 2077, they are all structurally mazes. Before we start to talk about algorithms, we need to have a basic understanding of the maze categories. We'll use the ideas when we do the analyze work at the end of the series, so this part is fairly important. The first one is what we call simple maze. Its characteristic can be summarized as follows. All cells in the maze can be reached, no loops at all, dead ends everywhere. From any point A to point B, exists one and only one path. The second one is called braided maze. This kind of maze does have loops, but in a strict definition, there should be no dead ends in braided mazes. This also implies that from any point A to point B, there's more than one path to go. There's also another kind of special category called recursive maze or labyrinth. Like its literal meaning, this kind of mazes usually consists of one path only. As long as you keep moving, you are definitely going somewhere. So this kind of design is very common to see in first-person shooting games. So when you are in the game, you may think, oh, this whole map structure is quite complex and stuff. But that's because everybody is busy shooting and killing people, so it's just nobody noticed that the whole structure is intentionally designed to be guiding and directional. Of course, this is only a general and vague division. We can see the whole scene as a spectrum, simple maze on one end and braided maze on the other end. Most of the mazes we can possibly see in real implementation is in the middle part of the spectrum. If you have more dead ends, then you are closer to be a simple maze. If you have less dead ends but more loopings, then you are more like a braided maze. In some part of the game, you can insert a recursive maze so that it doesn't really change the structure from a big picture, but at the same time, it's very easy to code and implement. You got the player running and shooting, they got a huge sense of achievement at the end and everybody is happy. So now we have the question, how exactly do the mazes get generated? Of course, it's not the designers who draw all of them line by line. The maze generation is a classic topic of the game algorithms. Depends on the game size, how complex you want the terrain to be. All types of algorithms have their pros and cons. For this episode, we'll talk about an algorithm that's really nice to use in small to medium games, recursive backtracking. This algorithm is based on a data structure called stack, so I will quickly introduce what it is. Imagine you have a set of tissue. The very top one is the last one to be put on, but the first one to be taken. So in computer science, you may arrange the data as chunks of tissues. In this data structure called stack, the order that you put in data and pull out the data is opposite. Okay, now we have a 4x4 two-dimensional space here. We can see how the recursive backtracking algorithm makes this area a maze. We'll use 0, 0 as the origin. For example, this is where we are standing. Then we can say that this 0, 0 cell has already been visited. When the maze is finished, we will see 4 times 4 equals to 16 check marks over here. The algorithm goes from 0, 0, and we can choose any of the connected neighbor cells for the next move. So in this case, it can be 1, 0 or 0, 1. Here we choose to go for 0, 1, so we put another check mark here and push 0, 1 on the top of the stack. We also put an arrow here to show that we go from 0, 0 to 0, 1. Then we repeat this step. Now we choose the next cell from the neighbors, can be 0, 0, 0, 2, or 1, 1. we see that from the right hand side, 00 has already been visited, so not under our consideration anymore. From the 2 cells left, we continue to go right, so our graph will look like this. We put a check mark and push the latest cell to the stack. So we continue in doing this, and at some point, we'll encounter something like this. We've gone to a dead end, and there's no next step anymore. So this is where we need to backtrack, and we can see from the visit history from the stack over here. From where we are now, we take one step back and pop the cell from the stack. But notice that the status for the cell is still visited, because it has already been included in the final maze. We'll see that much more clearly in the end. Okay, now we are back to this cell. Finally, new neighbors for us to pick, so we'll just give another try. So now we can see that from here, there are 16 check marks on the right, meaning all cells in the space have already been reached, so we're done with the backtracking algorithm. Here we can also tell another property of the algorithm, that is completeness. Wherever you start with, eventually all cells will be reached, no matter how large the maze is. Whether you define the neighbor to be 4 or 8, the algorithm is guaranteed to work. And the final step to actually draw the maze out is entirely depends on you. You can use the drawing tool from the engine or whatever available to you. Here I will just draw by my hand for simplicity. So we draw a line between all the cells with no arrow connection as walls. And we pretty much erase everything else. And then we got the mini size, cute and pretty, 2-dimensional maze. So you guys can imagine these walls go straight up to another z-axis, and we wrap it up with some good design, and that's pretty much what you can commonly see from the game. Here I only talk about the main idea of the algorithm. For the code implementation part, I put it to the next episode, so make sure to check it out. If you have any questions or comments, don't hesitate to let me know. Except for the maze generation, this kind of backtracking idea can also be used to make a little AI. For example, in a chess game, you need to predict all the moves the agent might possibly go and design your strategy. This implies some quite famous algorithm, but apparently that's like another new level of complexity, which I will also try to do tutorials in the future videos. In summary, as I said before, recursive backtracking is commonly used in small to medium games. They are easy to understand, straightforward to code, and is the default maze generation choices for many game developers. But the drawback is also quite obvious. If we have a huge map and we continue working for a long time and then hit a dead end, then all of this data before have to be stored in the stack, which is quite a lot of pressure for the memory. So how do these giant size mazes get generated? Is there another way to do this? The journey just started. Feel free to subscribe me for more content and like this video if you think it's helpful. I will see you guys very soon.